After 3 lectures on maximum flow problems, we are almost ready to call ourselves experts on network flows. The only issue is that the study of network flows goes beyond maximization problems or maximum flow problems. So recall that in a maximum flow problem, we have a source vertex S and a sink vertex T, and S has access to an unbounded supply of flow, and T has an unbounded demand for flow. And of course, the problem is, can we route flow from S to T? And the constraints that we have to respect are edge capacity constraints, so the amount of flow over a particular edge cannot exceed its capacity, as well as flow conservation constraints. And one observation that we made pretty early was that it's very easy to push 0 units of flow from S to T, and so inherently this set of constraints implies a maximization problem. And that's where we get the term maximum flow problem. But there actually are minimization problems that could apply to flow networks as well as problems that don't care so much about edge capacity and also don't consider a case where there's an infinite supply of flow available. What about cases where the supply of flow is finite? What about the cases where you don't care so much about the maximum amount of flow over an edge, but you care about things like minimizing cost? So one such problem is called the transshipment problem. And the transshipment problem is a type of resource distribution problem. And the resource in question could be something like electricity or water or goods. But of course, I'm just going to use the general term flow to refer to it. And you'll notice the vertices in this graph have annotations on them. So V4 has the annotation +3, V7 has the annotation -3. And it turns out that what's happening is in this network, there is a finite supply of flow. So consider an example where our resource that we're trying to distribute is electricity. And so suppose that city V4 contains a power plant, and some of the power generated by that power plant is used inside of city V4, but overall there's actually a surplus of 3 units of electricity. And then down here in V5, it turns out there's a shortage of 7 units of electricity. And we have this network of power lines, which are one way, and have an associated cost of transporting power through the network. And the question is going to become, is there a way of distributing the resource, of pushing flow through the network to balance out the cities that have a surplus with the cities that have a shortage? And so one obvious example of that is, if I wanted to, I could send the 3 units of surplus flow at V4 down to V7 via this edge here. And that would get rid of the surplus and get rid of the shortage. The edge from V4 to V7 has an associated cost, and that's a per unit cost. So if I send 3 units of electricity, I'm going to end up having to pay $9 for that. And maybe you can see already that there's a bit of a minimization problem forming. Not only am I asking the question, is there a way of balancing out the surplus with the shortage, but additionally, if there's a way of doing that, and maybe there are multiple options, I want to choose the one that costs the least. So this turns out to be a type of minimum cost flow problem. Okay, so I want to formalize this a little bit and then do a brief example and then come back and fully formalize the transshipment problem. So every vertex in this graph has an associated supply value, and that's the number that I've written underneath the vertex name. If I want to talk about that number formally, I will use the notation supply of V. And the value supply of V indicates the total surplus of flow at the vertex. So V4 has a surplus of 3, and V7 has a shortage of 3, because it has a negative supply value, a negative surplus. And notice that V1, V2, V4, and V8 have a net surplus, so +5, +3, +3, and +9. And actually, additionally, observe that the total surplus among all of the vertices in a graph that have a surplus is actually, okay, so 5 + 3 is 8, +3 is 11, +9 is 20. The total surplus is exactly 20 units. There are other vertices that have a net shortage, and so we've got V5, V6, V7, and V10, and observe that the total shortage among all of these vertices is actually -20. In other words, the total surplus in the graph and the total shortage in the graph cancel each other out. There are also 2 other vertices that I haven't discussed yet, so V3 and V9 have neither supply nor demand. They have no shortage or surplus. I haven't annotated them at all. Of course, that corresponds to a +0, I guess. They are already in balance in terms of their supply and demand. Now, I can route whatever resource I'm thinking of, so we'll just call it flow, but it could be electricity or water or goods. I can route that along edges between vertices. These edges have no inherent limit on their capacity, but they do have an associated per unit cost. I'm going to denote that cost by this, cost of UV. I'm also going to adopt the sort of soft convention that if an edge doesn't exist, let's find an edge that doesn't exist, there is no edge, for example, from V4 to V10, I'm going to adopt the convention that if ever I want to talk about the cost of an edge that doesn't exist, that cost is just infinite. The same way that when we talked about edge capacities a few lectures ago, I adopted the convention that the edge capacity of an edge that doesn't exist is automatically assumed to be zero or maybe negative infinity or something. This way I can talk about the cost of travel between any two vertices along an edge, even if that edge doesn't exist. We just adopt the convention that the cost of a non-existent edge is infinity. So, of course, unlike the maximum flow problem, where there weren't these per unit costs, and there were edge capacities, and moreover, there was an apparently infinite supply of flow, at least hypothetically, and there were dedicated source and sink vertices, this is quite a different problem. There's no specific source vertex with an infinite supply. Instead, there are some vertices that have a surplus, and some vertices that have a shortage. There's no dedicated sink vertex, nor are there edge capacities. But ultimately, this is still a problem involving pushing flow along edges in a network. And so this is basically still a network flow problem. And we're going to see that although it looks rather different from the problems that we're used to, it is actually pretty similar after all. Okay, so the vertices with a surplus, that would be these green vertices, V1, V2, V4, and V8, they sort of act like source vertices. In a sense, they're source vertices with a finite supply. So unlike the source vertices that we're used to in maximum flow problems, the total amount of flow that can be pushed through this network is limited by the total supply of the vertices with a positive supply value. And of course, that similarly means that the vertices shaded in red here, the ones that have a shortage or a net shortage, so a negative supply value, those act as sink vertices. And as I observed a minute ago, the total surplus in the graph and the total shortage in the graph happen to be equal to each other. There's a total surplus of 20 and a total shortage of 20 as well, which means, I guess, if I can find a way of canceling out all the surpluses by pushing the flow away, I should be able to, assuming the network is amenable to this, also completely resolve all of the shortages. And so the key constraint of the transshipment problem is, in fact, this global balance of supply and demand. Sure, there is an optimization problem involved. I want to minimize something. I want to minimize the total cost that I'm paying. But ultimately, the main constraint I'm trying to satisfy, the key constraint for anything to be considered a feasible solution, is I need to get rid of the surplus at every vertex and get rid of the shortage at every vertex. Now, I'll talk about this in a few minutes. There are extensions of the problem where the total surplus could be far greater than the total shortage. And you could argue that sort of makes the problem a little bit easier. In those extensions of the problem, it isn't necessary to completely eliminate the surpluses, but it is still necessary to eliminate the shortages. Okay, so a constraint I'm gonna add right off the bat to avoid having to talk about that extended case where the total surplus doesn't match the total shortage is I'm going to define a constraint for the basic transshipment problem called the net zero supply constraint, which is simply a way of stating that globally, across the entire graph, the balance of supply and demand is zero. So if I add up the supply value of every vertex, that summation should end up equaling zero. In other words, the total overall surplus in the graph should equal the total overall shortage. And if that is not satisfied, then we're not dealing with a valid instance of the problem. And so, of course, the net zero supply constraint requires that the total surplus exactly matches the total shortage, which means that the question that I was talking about earlier of, is there a way of shipping flow through the edges of the graph to get rid of every shortage, automatically implies, if such a routing exists, that there's also a way of eliminating every surplus. So the question then becomes, is it possible to route all of the surplus flow through the graph to satisfy the demand at vertices with a shortage? Now, if we can do that, then the question is going to become, is there a way of doing that cheaply? But I can think of some cases where it might not be possible to do that at all. And we'll talk about those in a few minutes, but one simple example of that is, suppose this edge didn't exist. Suppose there was no edge from V1 to V2. I guess I've been implicit about this so far, but one other constraint underlying this problem is that edge directions, of course, must be respected. So if I wanted to, I could send 3 units of flow from V2 to V3 along this edge, but I wouldn't be allowed to send units of flow backwards from V3 to V2, at least not on net. So we'll talk later about the policy of augmentation that we're going to see does allow this sort of notional backwards movement of flow, just like in our earlier analysis of maximum flow problems. But remember that these backwards movements of flow along augmenting paths, when we were talking about the Ford-Fulkerson algorithm, didn't literally correspond to moving flow backwards along an edge. It was more of a notional construction. So anyway, consider a situation where the edge V1, V2 doesn't exist. And now suppose that V1 has this surplus of 5 units. You'll observe that there's no way of getting rid of that surplus. I want to take that surplus and use it to satisfy a shortage elsewhere, but I can't because there are no edges that leave V1. And so in this case, there isn't a way of routing flow through the network to resolve all the shortages and also all the surpluses. And so this would be considered an infeasible instance. So I'll come back to that in a few minutes. The key thing is, before we begin talking about the cheapest way of balancing supply and demand, we first have to decide whether it's possible to balance supply and demand at all. Okay, so let's do an example of balancing out supply and demand. What I could do is I could take the surplus of 3 units at V4 and send it down to V7. And you can see that that would eliminate the surplus at V4 and satisfy all of the shortage at V7. Now, we need some notation to denote what I'm doing here, because the fact that V4 says +3 only tells me that V4 starts out with 3 extra units. If I'm going to be pushing flow around the graph, I need some way of indicating exactly what's happening so far. So what I'm going to do is, we've already seen that the supply value is the value written inside of the vertex. That is the amount of extra flow the vertex had starting out. As I ship flow throughout the graph, what I'm going to do with this second number outside of the vertex is indicate the total number of units entering that vertex, or the total number of net units entering that vertex. So with the routing I've just created, where 3 units are being sent from V4 to V7, the net number of units entering V4 is now -3, because there are 3 units leaving V4. The net number of units entering V7 is now +3. And you'll notice that in this situation, the number of units entering V7 is +3. The number of units that V7 needs is 3, so there's a shortage of 3, and that means that V7 is now balanced. It now has enough units entering it to satisfy the shortage. This also means that V4 is balanced, because all of the surplus is now leaving V4. Now, because I'm using the terms surplus and shortage, I think that there's a more urgent meaning to the word shortage. That is, it feels a lot less important for us to resolve a surplus than to resolve a shortage, because in our minds, if we think about a valuable resource, like electricity or something, it's of course a lot more important that a city that needs electricity gets it, whereas a city with a bit too much electricity, well, that can't be a bad thing, right? But remember that this problem is about balancing something. And so there are cases where the resource we're talking about is something undesirable. I mean, so for example, suppose V4 has 3 extra units of garbage, and V7 has 3 units of space in the landfill for more garbage. Well, then it is pretty important that I get rid of that surplus of garbage at V4. So keep that in mind, that our discussion of surpluses might implicitly sort of assume that they're positive, that they're a good idea. I mean, that's not helped by the fact that I'm literally using a positive sign to indicate a surplus here. But the key constraint of a transshipment problem is global balance. So without judgment to whether a surplus is bad or a shortage is bad, I want to fully resolve all surplus and all shortage. Okay, so I know the notation is getting a little bit dense here. The idea is that the number outside of the vertex is indicating the net amount of flow currently entering that vertex. Ultimately, what we're trying to achieve is a situation where the supply value of the vertex is the negative of the amount of flow entering that vertex. So here, that is happening, and it's happening for V7 as well. What I'm going to do is shade vertices that have achieved this balance in blue. So since 3 units of flow have been routed out of V4, and V4 had 3 extra units of flow, it is now balanced. And similarly, V7 is balanced. And in fact, if we look at the graph for a minute, we realize that all along, V3 and V9 have also been balanced, because V3 had no shortage or surplus, and so it was balanced to begin with. Okay, so let's try routing some more surplus units. I'll take one of those surplus units of flow at V2, and I will send it down to V6 via V3. Now, just like in maximum flow problems, I am allowed to route flow through a vertex because what's happening here is one unit of flow is entering V3 and one unit of flow is leaving V3. So V3 is not left with any net shortage or surplus and remains balanced as a result. So by sending one unit of flow from V2 down to V6, I've managed to balance out V6. Now, V2 is not yet balanced. V2 has a surplus of 3, of which 1 unit is currently being sent away, so I have to still get rid of 2 more units of flow from V2 before that will be balanced. Okay, so we could do that. Let's send 2 more units from V2 down to V3, through V6, and up to V5. Okay, so that fully balances out V2. There are now 3 units leaving V2, and V2 had an original surplus of 3, so it's balanced. V5 isn't balanced yet. It needs 7 units, but it's only getting 2 units. All right, so to get those extra 5 units, I can take 5 units out of V1, send them via V2 to V3, and then over to V6, and then up to V5. And this results in all 5 units of surplus at V1 being resolved, so V1 is now balanced, and as a result, V5 is also balanced. And so all that remains is to balance V8 and V10. And we can observe that actually V8 has a surplus of 9 and V10 has a shortage of 9. So as long as I can find some path from V8 to V10, we should be good. And it turns out I have one. So if I go from V8 over to V4 and then down to V6 and over to V10, I can send all 9 of those units from V8 to V10. And we can observe that as a result, every single vertex in the graph is now balanced. So we've now produced a balanced flow. If I work out the total cost of all of the routings that I've chosen, so for example, this edge here, I'm routing 3 units at a unit cost of 3, so that costs a total of $9. Here, I'm routing 8 units at a unit cost of 4, so this edge costs a total of $32, and so on. If I go and add that cost up for all of the edges in the graph, the total cost of the routing is $398. And so now we have an optimization problem. I know it's possible to balance all of the vertices. Is it possible to do so for a total cost of less than $398? Okay, so I can actually observe that the answer appears to be yes. So as before, we're going to have this problem of looking at this assignment and saying, okay, it meets all the constraints, it's a feasible solution, but how do I know whether it's an optimal solution? So what I want is to minimize something, so how do I know whether I have a minimum cost routing at this point? Well, it's actually pretty easy to prove that wrong if I can find a routing of lower cost. If I can find some way of achieving the same balance at lower cost, then clearly what I have here is not minimum. There is going to be a question later about, wait a minute, if I do have the minimum solution, how do I know? Because if I can't find a lower cost solution, I can't disprove that the current one is minimum. Maybe I'm just not looking hard enough. And so we noticed that with maximum flow problems, that was a rather difficult question to answer. In this case, though, the flow that we're currently looking at isn't minimum cost because I can come up with a cheaper way of routing some of the flow. So I can observe that currently 9 units are being routed from V8 down to V6 via V4. Now we know that those 9 units were originally routed all the way along from V8 to V4 to V6 to V10. But remember that if I can replace even a portion of my routing with some alternative routing that retains balance, and I can show that that saves cost, then I can show that my original flow wasn't minimum cost. So along the path from V8 down to V6, the unit cost of that path is $23. So I know I'm sending 9 units, but in the interest of keeping the numbers simple, let's just talk about the cost of sending 1 unit along that path. If I can find a path from V8 to V6 that costs less for 1 unit, then certainly it's going to cost less for 9 units. So the total unit cost of that path is $23 because it's $15 to get to V4 and then $8 to move onwards to V6. Okay, so $23, that's the best one I've seen so far. If I go looking elsewhere for paths from V8 to V6, I can observe that if I go down from V8 to V7 and from V7 to V5 and from V5 to V6, okay, that is a path from V8 to V6, and if I add up the unit cost of that path, okay, it's going to be $2 plus $2 plus $1, okay, that's $5. That's clearly a lower cost routing. So because the path of V8, V7, V5, V6 is $5, it makes more sense to send, instead of sending the 9 units to V4 and down, it makes more sense to send those 9 units along this path here. Okay, so I could make that adjustment. In fact, what I could do is just cross this off and write in 0, and then I could write 9 here and here and here, and sure enough, now I'm sending 9 units down this way. But for some reason, I don't want to frame the adjustment that way. I actually want to sort of actively adjust this flow in place. So instead of making it seem as if I'd never sent these 9 units to begin with, suppose we're already sending those 9 units, and I want to make the adjustment in a sort of live setting. Well, I guess what I want to do then is send back the 9 units. So the 9 units were already sent from V8 to V6, so I'll send them all backwards. Now, we're used to this idea. It's weird that I'm complicating things by bringing it up now, but trust me, I'm going somewhere with this eventually. What I want to do is take those 9 units that were already being sent from V8 to V4 to V6 and send them back. And of course, doing so will result in the amount of flow along those edges being 0. Once I've sent those 9 units back to V8, I will then send them forwards to V6 again, but I'll send them along this path instead. So what I can observe here is, maybe just by the choice of visualization, this does remind us quite a bit of augmenting paths from maximum flow problems. This looks a bit like a type of augmentation, right down to being able to push flow backwards along certain edges. And one other observation that I want to make is that if I have, let's say, this edge here, I'm currently sending 9 units along this edge here at a unit cost of $8. If I send back any of those units, so again, if we assume the 9 units are already getting to V6 and I am sending them back, what is the cost of the reverse direction of travel? I would argue that it's negative $8. I actually save $8 every time I send a unit back, because sending a unit back is equivalent to not having sent the unit at all. And so if sending it costs $8, then, not sending it will save me $8 versus the scenario where I do send it. And so what I'm building up to here is that what I've done really is a form of augmentation. I have modified my flow in such a way that balance is retained, because you'll notice that what I've basically done is sent the flow in a circle. And because I've sent it in a circle, the overall balance of flow in the graph doesn't change. It's just that the routing the flow takes changes. And as a result, I get a lower cost routing after this essentially augmentation along a cycle. Okay, so sending those 9 units back along the path V6, V4, V8 results in a savings of $23 per unit, because the cost of the forward direction is $23 per unit, and returning those units to sender just gives me an equivalent savings, so a savings of $23 per unit. And so in general, we will define, and we'll come back to this definition later and do it more formally, we will define the cost of traveling backwards along an edge to just be the negative of the cost of traveling forward. So if it costs $8 to send a unit of flow in this direction, and I'm already sending that unit of flow, then the cost of sending that unit of flow back, which is equivalent to not having sent it at all, is just the negation of the cost of the forward direction. So once I've sent those 9 units back, I can resend them from V8 to V6 via the lower cost path through V7 and V5 at a per unit cost of $5. Therefore, the per unit cost of the adjustment is, well, the savings of sending those 9 units back plus the cost of sending them forwards again, which is a net savings of $18 per unit. So what I found, in a sense, is a cycle in this graph, an augmenting cycle in this graph, whose net cost is negative. A negative cost cycle. So total cost of the routing after my adjustment is now $236, which is certainly an improvement over the $398 I had before. And of course, that leads us to the question of what is the minimum cost? We've now seen that we could find a routing that balances supply and demand, and then we could find another routing that also balances supply and demand for cheaper. And so the question is this routing the minimum cost? And what is the minimum cost of any routing, and how do we know when we have it? Okay, I want to take a step back now and formally define the transshipment problem. Now that we've seen the example, we've got a sort of feel for how the problem works, let's formally define it. So the transshipment problem involves finding a minimum cost routing such that all vertices are balanced. And we can view the requirement that vertices be balanced as a constraint. And so if this constraint is not met, we don't care about the cost of the routing. We only care about costs of routings if the constraint is met. So an instance of the transshipment problem is a directed graph G with a cost function defined along edges. So we could view we could view this cost as being a weight along the edge or something similar. So similar to the type of flow network we use for maximum flows, we could view that flow network as an edge-weighted directed graph or as just a regular directed graph with a couple of functions defined to tell us things like edge capacities and the flow value along an edge. To avoid notational confusion, although this is a fully valid form of flow network, it is an example of a network flow problem, I am generally going to call this type of thing either a transshipment instance or maybe just a directed graph. You'll notice I've called it a directed graph here because I guess that way if I say flow network, we can assume I'm still talking about the type of flow network we worked with in the previous few lectures, which would be for the maximum flow problem. Okay, so a transshipment problem is a directed graph where I have a cost function defined along edges and a supply function defined for every vertex. And for a transshipment instance to be valid, we want that net zero supply constraint to hold. Of course, there are extensions of the problem that allow the total supply of the graph to exceed the total shortage, in which case you can achieve balance in a variety of other ways. There might be more degrees of freedom for how you achieve balance. We're not going to worry about that. So it's not too difficult to define that extension. We're going to focus only on transshipment instances where the total supply, the net supply of the entire graph, is equal to zero. So if I talk about a transshipment instance and this does not hold, it is not a valid instance. I shouldn't try and solve the optimization problem at all. And now, as I said, I will tend to call graphs like the one on this slide transshipment instances or directed graphs with cost functions instead of flow networks, even though it is a type of flow network, just so that way in this course, when I say flow network, I can always be referring to the classic maximum flow style flow network with a source vertex and sink vertex and edge capacity constraints. All right, so if I want to talk about the optimization problem I'm solving in the transshipment problem, let's let f of uv denote the total flow across every edge. The objective of the transshipment problem is to find a function that minimizes the total cost of the flow. So I'll define cost of f to equal the sum of just multiplying the amount of flow along each edge by the cost of that edge, subject to the following constraints. So this minimization only applies if certain constraints are met. And the constraints are, first, that edge directions are respected. So there is no maximum capacity along every edge, but we do still require that if you would like to use an edge, flow must be pushed in the forwards direction of that edge. We're allowed to make adjustments that look like backwards flows. So if I have 5 units of flow being transported in the forwards direction, I might make an adjustment that to me looks like I'm pushing flow backwards. But at the end of the day, I'm required to push a positive amount of flow along each edge only if the edge exists. So I can't push flow between vertices where there is no edge, obviously. And then also, I require the balance constraint, which ultimately amounts to this idea, if we scroll back to our example here, that the total amount of flow leaving a vertex or entering a vertex is the opposite of the shortage or surplus at that vertex. So a vertex with a surplus of 3 should end up with 3 units leaving it in my balanced flow. And a vertex with a shortage of 3 should end up with 3 units entering it in a balanced flow. And we can frame that sort of like this. What you will observe is that this looks a lot like the flow conservation constraint from the maximum flow problems. The difference is the right-hand side isn't 0, the right-hand side is the supply value for the vertex. That actually might be the beginning of a tip-off that maybe these problems aren't so different after all, because the constraints are very similar. I mean, that is, this is still a linear constraint relating to the amount of flow, the net amount of flow entering or the net amount of flow leaving the vertex. The difference is only what's happening on the right-hand side. And the value on the right-hand side here is the supply of V, which is, with respect to the optimization problem, a constant. So something to think about, the fact that actually the constraint system for the maximum flow problem isn't really that different in a lot of ways from what we've defined here. Okay, so if both of these constraints are met, if flow is always flowing in the correct direction along edges, and all vertices are balanced, we would like to find a flow that satisfies those constraints and minimizes the total cost of the flow. We'll take a look at a few instances just to illustrate cases where constraints don't hold. So first, let's look at an instance that we would not consider to be valid at all. So here on this graph, if we take a look at the net surplus in the entire graph, it's 13 units. but the net shortage is only 8 units, which means it's impossible to achieve perfect balance because the global net supply is plus 5. There are 5 extra units of flow in this graph that we couldn't get rid of. Now, although there are extensions of the problem that would allow us to solve it in this case, we're not thinking about those. We do actually have to be careful how we define such an extension. And so we would consider this to be an invalid instance. We don't even try to solve it. It is invalid because there's not a global balance of flow. And so here's the slide saying what I just said about there existing maybe extensions of the problem that we could solve. We're just not going to focus on those. Okay, so in this graph here, the net supply does turn out to be 0. So notice how the net surplus is 8 and the net shortage is also 8. Okay, so all looks good so far. However, if we try and solve this, we're going to discover that no balanced flows exist at all. So it doesn't make sense to try and minimize the cost because there is no balanced flow to begin with. We can actually argue in this case that the minimum cost of balancing supply and demand is infinity because there is no way to balance supply and demand. And the reason is similar to what I showed off earlier, which is that I have a vertex in the graph with a net surplus, but with no outbound edges. So what am I going to do with those 5 extra units of flow? I have no choice. I've just got to keep them at V1 forever. And of course, that's a problem because that means I can never balance V1, but it also means that at least one of these other 2 vertices also can't be balanced because I'm going to need those 5 units of flow to balance out the vertices V2 and V5. So although this is a valid input instance because the net zero supply constraint is met on the input graph, it's infeasible. There is no solution whatsoever, so there's no way of minimizing the cost, and therefore we could argue that means that the minimum cost is just infinite. Now, the converse case, I suppose you could argue, well, wait a minute, if there's a case where the minimum cost is infinity, is there a case where the minimum cost is negative infinity? And the answer is yes, and it would show up in a case like this. So here is a transshipment instance that does have a global balance of supply and demand, so again, 8 units either way, and it does turn out that there are balanced flows. There is a way of routing flow between all the vertices such that all of the surpluses and shortages cancel out. The problem is this graph contains a negative cost cycle. And you can see that what that means is that if I just route 1 unit of flow around the negative cost cycle more or less forever, I can continue driving down the minimum cost of the flow, which means there is no minimum cost. Although there are ways of balancing the flow, it doesn't make sense for me to ask the question, what is the minimum total cost I will have to pay? Because in fact, I can make it arbitrarily low. Now, as usual, I am going to observe that there is nothing inherently wrong with having a negative cost along an edge. In a lot of ways, the way this problem is most intuitively framed makes us feel like it makes no sense to have a negative cost along an edge, because we think of stuff like, oh, if we're transporting something from V2 to V1, that obviously has to have an associated positive cost. Maybe it's free, but it doesn't make sense that somebody would pay us to do it. But there are cases where we choose to model a problem where that actually could be a negative cost. Somebody could actually pay you to use a particular edge. It's similar to what I said earlier about how we tend to view the idea of a surplus as a positive thing. We think, oh yeah, you've got a bit of extra water or a bit of extra goods or something in vertex V1. No big deal. It's more important that we get rid of this shortage. But remember that this is just resource distribution. And so if the resource that I have, again, is something like garbage that I want to get rid of, then that surplus actually is a bit of a problem. And the same thing is sort of true about edge costs. There's nothing inherently wrong with the cost of an edge being negative. There is a bit of a problem if there's a negative cost cycle, although the problem isn't really that severe, because in a sense, it is possible, therefore, that I can make a huge amount of money by routing flow around the cycle, sure, but that doesn't mean that there's no way of balancing supply and demand. It just means that the question of the minimum cost of balancing supply and demand is a bit of a ridiculous question. In any event, there is no solution, no optimal solution in this case, because the cost can become arbitrarily low. We could therefore argue that, at least conceptually, the cost is negative infinity dollars. So I could make infinite profit by just running 1 unit of flow around this cycle forever. It turns out that there are a variety of algorithms to solve minimum cost flow problems, and if we wanted to, we could go and spend 3 lectures talking about how to solve minimum cost flow problems. One algorithm, the one that I'm most familiar with for solving minimum cost flow problems, is the network simplex algorithm, which is a variant of the simplex algorithm, which is a incredibly important algorithm in the field of linear programming to solve linear programs. And basically, the network simplex algorithm is a specialized linear programming solver. Now, I just said we could spend 3 lectures talking about how to solve minimum cost flow problems. I now realize that if you actually want to do that, you can just go right ahead and look up my videos for the network simplex algorithm, because I think there are 3 of them. So there you go, if you want to do that. But that isn't really the point of this application today. So I said at the beginning that we are now experts on the maximum flow problem, and I want to make the case that we're experts on network flow problems in general. And so although we could go and learn algorithms to solve minimum cost flow problems from scratch, the main case that I want to make today is that we actually already know almost everything we need to solve minimum cost flow problems, because it turns out it is possible to solve minimum cost flow problems using specializations of the algorithms that we already know. In particular, we can specialize the Ford-Fulkerson algorithm to solve the transshipment problem. And I believe that if I can show that off, that is a pretty good argument that even though we're only really specializing on maximum flow problems in this course, it actually does make us experts on network flows in general. So to do that, I want to rewind a bit and go back to talking about the flow networks that we know and love from the last few lectures. So consider this specialized flow network. It's got a source vertex, it's got a sink vertex, it has edge capacities, everything looks nice and comfy as far as that's concerned, so it's exactly the kind of flow network that we're used to, except that every edge now has a cost. And we could view this as some sort of fusion between a maximum flow problem and a minimum cost flow problem. We've already seen that there could be multiple distinct maximum flows in a flow network. So the question then becomes, if I find a maximum flow, is there a way that there might exist some other maximum flow that has lower total cost? And that's the direction I'm going to go in to show that there actually is a way of solving minimum cost flow problems using the algorithms that we already have. So consider this flow network, which is an ordinary flow network, the kind we've seen over the past 3 lectures, except that every edge also has an associated per unit cost. And just to give an example of that, the per unit cost of the edge V1, V6 is $2. And so, as I mentioned earlier, if you push 2 units of flow across that edge, the total cost is going to be $4. So 2 units of flow times $2 a piece. Now, I could go and compute a maximum flow for this flow network, and I've done so. It turns out that the value of a maximum flow is 18, and the cost is a rather steep $1,258. And so I happened to compute this maximum flow using the Edmonds-Karp algorithm. We know by now that there are lots of other ways of doing that. I could use the generic Ford-Fulkerson algorithm as well. In any event, once I'm done computing a maximum flow, whether it's this one or some other maximum flow, it will definitely have a value of 18. But since I'm talking about the cost, because I have these per unit edge costs, I guess there is a natural question of, hey, wait a minute, there could be more than one maximum flow. So more than one flow with total value 18. Is there one whose total cost is less than $1,200? So I can compute the total cost using logic we already discussed in the context of the transshipment problem. The cost of a flow F is just equal to the sum of the cost of the flow across every edge, which itself is just the flow across the edge multiplied by the cost of that edge. So the natural question is there a way of routing 18 units of flow from S to T, so still having a maximum flow, such that the total cost is less than $1,258? Here's a good time to pause the video and stare at this network for a minute and decide whether you think the answer is yes. I'll just have a sip of my beverage here. That's refreshing. I'm assuming you've had a chance to think about it. So my eye goes immediately to that edge there. I'm not a big fan of paying $1,200 for a flow. And if I go looking at where the culprit is in this graph, I would say this edge is pretty pricey, $100 per unit. And so I stare at that. And I think if I could find some way of routing at least a portion of those 10 units via some other means, I could probably save money. Because if I stare at the other edges in this graph, none of them have a cost even close to $100. So even if the way of avoiding this edge requires taking a whole bunch of different edges, I probably still will save money. And you might have also noticed, if you notice this edge seems to be the source of a lot of my problem, because I mean 10 units at $100 a piece, that's making up the vast majority of this high cost. You probably also noticed that if I routed flow from S to V3, and then up to V1, I could convey all 10 of those units to V1 without using this edge at all. So before we talk about how to improve the flow, I guess I have to define some things so that we have a problem that we're actually trying to solve, a formally specified problem. So what I asked was, can I find a flow with value 18 whose cost is less than this? I don't want to change the value of the flow, I just want to change the cost. So define, in the context of a maximum flow problem with edge costs like this one, define a minimum cost flow to be a feasible flow f such that the cost of f is less than or equal to the cost of any other feasible flow with the same value. And this is a key thing. And you'll notice that I'm just saying define a minimum cost flow. So in the context of this lecture and in this course, when we talk about flows, we will be talking about this style of flow network with a source vertex and sink vertex with edge capacities like a typical maximum flow problem. So a minimum cost flow, as far as we're defining it here, is defined over the style of flow network that we've already been working with. We'll see later how we could use this definition to solve instances of the transshipment problem. The key thing about our definition of minimum cost flow is that it's value neutral. That is, a minimum cost flow is a flow of a particular value that has the lowest cost among all other flows of the same value. I'm not allowed to change the value at all. Now, congruently, what I was specifically talking about wasn't just a flow of value 18. It was the fact that the flow of value 18 that I found is a maximum flow. I mean, I used the Edmonds-Karp algorithm to find it. So let's define a minimum cost maximum flow, it's a bit of a tongue twister, to be a maximum flow such that the cost of that maximum flow is less than or equal to the cost of any other maximum flow on the same network. So the task then that we have to solve today is develop an algorithm to find a minimum cost maximum flow given a flow network like this one with associated edge costs. So one idea, there are actually sort of two ways we could tackle this. We could start by finding some maximum flow and then iteratively reduce its cost without reducing the value. So basically cycle through various different maximum flows until we find the one with lowest cost. I think that's the option we should pursue first. It's not the only option. The other option, instead of cycling through a bunch of different maximum flows, the other option would be to cycle through a bunch of different minimum cost flows whose value changes and slowly work our way up to a flow of maximum value. We are going to talk about that later. Okay, so if we go back to that edge that I think was causing some trouble, what I can observe is that we're currently sending 10 units from S to V1 at a whopping $1,000 in total, where we could be sending them to V3 and then up to V1. There is plenty of capacity available to do that at a total cost of only $100. So in other words, we get a total savings of $900 from doing that. That might not get rid of all of our wasted money in this case, like there could be other ways of saving, but certainly that would save us a lot of money, so we should start with that. Now, the question is, how do we frame this adjustment? And if we think back to earlier with the transshipment problem, I said, yeah, you could just say, pretend I never sent those 10 units and then send them along this edge instead, sure. But I want some formal way of framing how I'm moving between these two maximum flows. Hopefully you can observe that if I send the 10 units via V3, that the total value of my flow doesn't change. The same 10 units are still reaching V1 just by some other path. And therefore I will still have a maximum flow when I'm done. And it's pretty clear I'm going to have a lower cost maximum flow as well. So the adjustment that I'm doing, if I can find some way of formally framing it, might give me a hint as to what algorithm I might use to do this. So I don't think that it's as simple as saying, oh yeah, right, I never sent those 10 units. Pretend you didn't see that. I actually want to have an active adjustment. I'm already sending 10 units. I want to say, I want to send those 10 units back. So send them backwards from V1 to S, and then send them forwards to V3 and up to V1. In other words, create what looks a lot like a cycle. Okay, so I send those 10 units back from V1 to S. That creates a shortage at V1 of 10 units. Hey, that's right. With maximum flow problems, we are actually used to thinking about shortages and surpluses. Only in a typical maximum flow problem, you're not allowed to have a shortage or surplus at an intermediate vertex. But interesting that we already have the notation and the logic for such a thing to exist. Okay, so I send those 10 units back, and then I send 10 units forwards along the path V3, V1 from S. And we can observe that doing so resolves that shortage. So the shortage of 10 units that I created by sending back those 10 units is immediately resolved if I then send the same 10 units back to V1 by some other path. Now observe that if I use our typical augmentation notation here, what I really have is basically an augmenting path that begins and ends at the same point. We could argue it begins and ends at V1 because I started by sending units backwards from V1, or we could argue that it begins and ends at S. It doesn't make much of a difference where we think it really begins and ends because it goes around in a circle, where we send 10 extra units up to V1 and then return 10 previously sent units down to S again. So this entire adjustment that I just did, which did not change the value of my flow, but did reduce the cost, is basically an augmentation around a cycle. And the fact that it's a cycle, because the augmentation begins and ends at the same vertex, the total amount of flow in the network is unchanged, because every unit of flow that leaves V1 at one point in the cycle then re-enters V1 later. And the same is true with every other vertex. Every unit of flow that enters V3 also leaves V3, which means the total balance of flow in the network is unchanged. We also know, the reason we chose the cycle that we did was that it was lower cost. And so because the value of the flow is unchanged, since the balance of every vertex is unchanged, we know that the result of this modification is a lower cost maximum flow. We still have a maximum flow, but it's definitely one of lower cost than we had before. So what I want to do next is find some way of showing that once I've reached a state where I can't perform any more of this type of adjustment, that I actually have a minimum cost flow. Now to do that, of course, the first thing I need to do is to formalize this type of adjustment. So to do that, let's go back to talking about residual networks, because you've already seen this during this lecture, even in the discussion of the transshipment problem. There are a lot of numbers on these diagrams. This is not a very easy problem to solve on paper at all. And it's certainly not very easy to solve if we have to think about walking along edges backwards at a negative total cost or something like that. Having a residual network on hand makes this a little bit easier. Okay, so let's consider this flow network, which has associated per unit costs, and the associated residual network. Now at the moment, because we're working with the all-zero flow, the two networks are identical. We haven't pushed any flow through the network yet, and therefore it's not possible to consider pushing flow backwards along an edge. Let's just choose some augmenting path. So the flow I'm going to come up with here isn't a maximum flow yet. It's just some flow where I am pushing something from S to T. So the path SV1 V5T is an augmenting path, and the capacity of that path, as you can see, is 5 units. Let's perform an augmentation along that path. Okay, so I do that, and then once I perform the augmentation, notice that this edge here is now saturated. And we know already that what that means is that in the residual network, it will certainly no longer be possible to push anything from V1 to V5 because the edge is saturated. However, I am allowed to push flow backwards from V5 to V1 to deplete the flow that's already moving in the forwards direction. And so an edge appears from V5 to V1 in the residual network. Okay, that shouldn't surprise us. We already know about that. The point I want to bring up is how much does it cost to push flow from V5 to V1? Well, really, we know that there's no such thing as pushing flow backwards. At the end of the day, what we're actually doing when we talk about pushing flow backwards is just canceling out units of flow being pushed in the other direction. So at the moment, each unit of flow being pushed from V1 to V5 costs $3. So in the current configuration, it costs a total of $15 to send all 5 units from V1 to V5. Suppose I sent one of those units back. So suppose I sent one unit backwards from V5 to V1. Well, that would result in the total cost, in the total number of units being 4, and the total cost being $12. In other words, the net cost of sending something backwards from V5 to V1 was negative $3. I'll write that like this. Negative $3. And so I would argue that it's pretty natural to say that when you see this reverse edge pop up in a residual network, well, we're talking about networks with costs, which means we do sort of need to assign a cost to every edge. And the cost of the reverse edge should just be the negation of the cost of the forwards edge. So the edge V1, V5 costs $3, so the edge V5, V1 costs negative $3. Because when I'm pushing flow from V5 to V1, really what I'm doing is canceling out flow that's going in the opposite direction. Okay, so I mentioned that, I alluded to that earlier in the context of the transshipment problem, but now we can see it firsthand. With the context of the residual network, I think it's pretty clear why we have to make this definition. So the cost of pushing flow backwards along an edge is just the negation of the forwards cost. So the cost of V5, V1 is negative $3. Now, there is actually an issue cropping up here, and it has to do with my very bombastic demand 3 lectures ago that we be allowed to consider very general flow networks. So, for example, I talked about 3 lectures ago the fact that some sources say things like you're not allowed to have bidirectional edge pairs at all in a flow network, although this is actually a pair in the residual network, so it's not a big deal. And you're not allowed to have things like edges that point towards the source vertex or away from the sink vertex. And I argued that that's not a good idea because it restricts the problems that we can model. Okay, so it's going to come back to bite me here. So for this lecture, what I'm going to say is that the cost calculation I'm describing becomes a little bit more annoying in cases where the original network has bidirectional edge pairs. So if the original network had an edge from V5 to V1 and the cost of that edge was different than the forwards cost, it wouldn't actually change the solvability of my problem, but it would make the cost calculation rather annoying, because that means the cost of sending a unit backwards along the edge V1, V5 is different than the cost of sending a unit of flow forwards along the edge V5, V1. There's no reason why that actually changes that much in the grand scheme of things, but it does make our lives a lot harder as far as learning about the problem. And so in this lecture, I'm going to assume that the flow networks that we work with do not have bidirectional edge pairs in the original network. They're still going to show up in the residual network, that's just fine, but they're not going to be in the original network, because if they were, and the cost of a bidirectional edge pair was asymmetric, something weird would happen. None of the algorithms that we develop actually have a problem with that, but the implementation you have to write has to be a little bit more careful about how it's pushing flow and how it's determining costs if we do that. So keep that in mind. The pseudocode that I show later on will be tailored to the case where the original network doesn't have bidirectional edge pairs. Okay, so what I've done so far in this graph is I've pushed 5 units of flow from S to T. This is not a maximum flow. It's hopefully relatively clear that there exists at least one other augmenting path that would allow me to increase the value of the flow. That's not what I care about, though. So suppose that I consider flows with value 5. Is there a flow with value 5 that costs less than $145? That's really what I'm asking. Is it possible to reduce the cost of this flow that I have here without changing the value of the flow? And the answer turns out to be yes. If we go over to the residual network, what we can observe, and again, this is something that is not very easy to do by just general inspection. So unlike a lot of graph theoretic things we've seen in the past, this is something where you really do have to go looking for these in some cases, because negative cost cycles aren't something that just jumps out at people. But we can observe that in this residual network, there is a negative cost cycle. And basically, it's driven by the fact that the edge from V5 to T in the original network costs so much. I'm pushing 5 units from V5 to T, which means if I start pushing those units backwards, I begin saving $25 a unit. And so if I try that, so if I go from T to V5, down to V3, over to V4, and back up to T, that's a cycle, and the total cost of that cycle is very clearly negative, because it's negative 25 plus some pocket change, pretty much. So what I have is a negative cost cycle in my residual network. And notice how previously when we saw negative cost cycles, we were talking about minimum cost paths a few lectures ago. And in the context of minimum cost paths, negative cost cycles were a bit of a disaster. We argued that they rendered the entire instance of the problem unsolvable. But in this context, a negative cost cycle isn't so bad, because the edge capacities thwart the usual problem induced by negative cost cycles. So in the context of minimum cost paths, the reason why negative cost cycles break things is that if we go around the negative cost cycle forever, we can drive costs down arbitrarily low. And we saw that earlier in the transshipment problem. That isn't going to be a problem with this negative cost cycle, though, because edge capacities do limit the total number of times I can use the cycle. The maximum number of units of flow that I can push around this cycle is 2. Just the capacity, if you think about this cycle as a sort of augmenting path, the capacity of that path is 2, because once I've pushed 2 units from V5 to V3, the edge is saturated and the cycle becomes inoperative. So if I do that, though, if I push 2 units around this cycle, I will have a net savings. Okay, so I'll perform an augmentation around that cycle. So I view the entire cycle as a form of augmenting path. I push 2 units from backwards from T to V5, and that's a savings of $50. And then I push them down to V3 at a total cost of $2, to V4 at a cost of $4, and back up to T at a cost of $1. And this does produce a lower cost flow. So I go from a cost of $145 in total to $103. And so what I've done is effectively an ordinary augmentation, but it's around a cycle. And so let's define that to be an augmenting cycle. Any cycle in the residual network with non-zero residual capacity is an augmenting cycle. I should actually say that again. So if it's a cycle in the residual network, it automatically has non-zero residual capacity. It turns out this is a redundant way of framing it. A cycle, an augmenting path in the original network that happens to be a cycle is an augmenting cycle. And any cycle in the residual network with negative cost turns out to be one of the ones that we want, although actually I'm getting a bit ahead of myself. In general, an augmenting cycle doesn't have to have negative cost. We care about augmenting cycles with negative cost for our purposes, but any cycle with non-zero residual capacity is an augmenting cycle. Okay, let's let the slides catch up to my definition. So formally, an augmenting cycle is some sequence of vertices such that if I look at any pair of vertices along the way, so any consecutive pair of things like qi plus 1, the residual capacity between qi and qi plus 1 is greater than 0. Notice that unlike our definition of augmenting paths from, I guess, lecture 37, there is no requirement that an augmenting cycle involve the source vertex or the sink vertex at all. An augmenting cycle could occur completely away from the source and sink vertex. And now we can actually move towards characterizing minimum cost flows. If the residual network has an augmenting cycle and the total cost of that augmenting cycle is less than 0. So remember that an augmenting cycle itself doesn't have to have negative cost. I got a bit tongue-tied a minute ago because I got ahead of myself. An augmenting cycle is just an augmenting path that is a cycle. It doesn't even have to start or end at the source or sink. But if we have an augmenting cycle with negative total cost, then that means that the flow you're looking at is not a minimum cost flow. Because if you can find some augmenting cycle with negative cost in the residual network, that means there's a way of sending flow around in a circle, preserving the balance of flow such that you save money. So that must mean that there exists some flow out there with the same value but lower total cost. And so the basic argument is, look, if you have a negative cost augmenting cycle and you perform an augmentation along that cycle, then you're going to get a flow with the same value because the flow remains balanced, and the cost of the new flow you end up with after augmentation is going to be the cost of your original flow plus the residual capacity of the path multiplied by the cost of the path. But we know the residual capacity is greater than 0, and we know the cost is less than 0, which means that this sum is going to be less than the cost of the flow you started with. And of course, that means that the flow you started with wasn't a minimum cost flow. Okay, so the question then is, well, we've got this flow here with total cost $103. Is this a minimum cost flow? Now, normally this kind of comprehension question is the kind of thing we could answer by sort of staring at the residual network and going and looking, but I would forgive you for not being able to find the answer directly because there's a lot going on here. So we'll just skip to the answer. It turns out that the answer is no. There is still a negative cost cycle, and it's not the most obvious thing in the world. So I can go from T to V5, down to V1, up to V3, over to V4, and back up to T. And the cost of that cycle is negative $23, which means there is a way of saving money by pushing flow around in a circle and preserving the balance of flow and therefore the value of the flow that I have. So I perform that augmentation and my total cost drops from $103 down to $34. That's pretty good, okay? The flow is actually still not minimum cost. We'll go through the next bit pretty quickly here. It turns out that there is still a negative cost cycle. Notice that this negative cost cycle from V3 to V5 down to V1 and back up to V3 doesn't involve S or T directly. So it's a cycle completely away from S or T. If I send some flow along that cycle, it looks like the capacity of the cycle is 2, then I can save $2 per unit. Okay, so I do that. I perform that augmentation, and the total cost of my flow of value 5 is now $30. Okay, so it turns out at this point, and again, it's not the easiest thing in the world to verify this because there are so many edges, and there are still some negative cost edges, but it does turn out that there are no negative cost cycles in my residual network at this point. Does this mean that we have a minimum cost flow? And think back to lecture 37, where we had the same question about maximum flows. We reached a point, we had defined an augmenting path, and we reached a point where there were no more augmenting paths. We had no way that we could see of pushing more flow through the network. And the question was, Does that mean we found the optimal solution, or does it mean that we're not looking hard enough? And so we have the same question here. And in fact, if we'd covered flow problems from the beginning using minimum cost flows and worked our way up to maximum flows later, we would now have to go through the whole process of proving some theorems to tell us when we have a minimum cost flow. Because for the sake of this lecture, we're mostly doing an overview of the topic, I'm not going to feel too obligated to present detailed proofs of things, but it turns out that the answer is yes. It turns out if you reach a state where there is no negative cost cycle in the residual network, that you have indeed found a minimum cost flow. And so we'll state a theorem for that. Suppose you have a flow network with associated edge costs, and suppose you have a feasible flow such that the residual network has no negative cost cycles. In other words, the graph has no augmenting cycle of negative cost. In that case, F is a minimum cost flow. Now, as I said, because we're approaching this more as an overview of minimum cost flows, we don't need to slog through the proof. But actually, as it turns out, proofs of this theorem tend to be things that we aren't really equipped to prove in this course anyway. So I've looked at a variety of sources, and in general, when it comes time to prove this fact, it tends to be proven using linear programming. So in other words, it tends to be proven not using the network itself, but using the duality theorems from linear programming. Now, the duality theorems from linear programming are a really big deal. It actually turns out that you could also prove the max flow min cut theorem directly from linear programming duality. We can actually view the max flow min cut theorem as a special case of linear programming duality. All the more reason to go take a linear programming course. I have seen a couple of proofs that do attempt to prove it directly using the flow network, but they're very tedious. And actually there's one source I looked at that doesn't even bother giving much of a proof. Its one sentence proof is, well, it's pretty obvious, pretty much. The one sentence proof I've seen in one source amounts to, look, if you have a graph with no negative cost cycles, then if there were a flow of lower total cost, you could get it through a series of augmentations, which is an interesting observation, but a really weird thing to state without proof. It's the kind of thing you do sort of have to prove. I found some sources that do prove it with what appears to be an actual rigorous proof using flow networks. And so the idea there is, suppose that you don't have a minimum cost flow. So suppose F meets the criteria of the theorem, but isn't a minimum cost flow. Consider some other minimum. So suppose there is a minimum cost flow that has a cost less than F. So it has the same value as F and total cost less than F. As I said, one of the sources I looked at basically says, look, if such a thing existed, you could get from F to F prime via some augmentations. And therefore, that's impossible because there are no negative cost cycles or something like that, which again seems a bit circular. One source I found said what you could do is look at the difference, basically, between the flow F prime, the hypothetical flow F prime and F, and show that essentially that requires that there exist a cycle. I guess the overarching logic there is there has to be at least one edge where the amount of flow along the edge is different between the two flows. Otherwise, they're the same flow, obviously. And if the amount of flow along that edge is different, but balance is maintained, then in a broad sense, and this is why it gets tedious because there's a whole bunch of special cases, in a broad sense, that means that whatever unit of flow, so for example, if this used to have 5 units on it in the original flow F, and in F prime it has 3 units, well, that sort of means there has to be some way that the other 2 units are still getting to V, a path of lower cost. And essentially what you can observe is if you take that path and fold in this edge, you must have a cycle, and that means that you have a contradiction. So we're not going to do that proof. What I will observe is I've looked at a bunch of options for proofs. Some of them seem to be cop-outs. A bunch of them seem to be using linear programming duality, which we don't know about. And the ones that use the graph directly, the ones that would be accessible to us, are very tedious. And in any event, we want to get this lecture over with in one sitting. So we'll just state the theorem and say it can be proven. I'll have some references that I provide if you want to take a look at the proofs and see whether you agree with me about what I just said. So because of that theorem, because of Theorem A, we can conclude that since there are no negative cost cycles in the residual network, that the flow that we found of total cost $30 is a minimum cost flow of value 5. Now, it's not saying that there are flows of value 7 that have costs less than $30 or something, or more than $30. It's just saying only among flows of total value 5, this is a minimum cost flow. So, of course, our definition of minimum cost flow is related to flows of a specific flow value. And of course, the theorem also basically gives us an algorithm to find a minimum cost flow. We just start with any maximum flow, and that maximum flow may not be a minimum cost flow. If I want a minimum cost maximum flow, I start from any maximum flow. I then look at the residual network. If it contains a negative cost cycle, I perform an augmentation and try again. And I keep doing this until I end up in a state where the residual network does not have a negative cost cycle. And when I'm there, by the theorem, I must have a minimum cost maximum flow. Okay, so in the first phase of the algorithm, I go compute any maximum flow I want. And the idea is that the process we've just discovered of using these negative cost cycles always preserves the value of the flow. So if I start from a maximum flow, I will end up with a maximum flow when I'm done. So we know already we can compute maximum flows in polynomial time, for example, with the Edmonds-Karp algorithm. Okay, great. So I can do that. That's phase one. In the second phase, I take my maximum flow and I keep performing augmentations along negative cost cycles in the residual network until there are no negative cost cycles, at which point, by Theorem A, the flow I have must be a minimum cost flow, and since it was a maximum flow, it is a minimum cost maximum flow. Now, I guess a natural question here is, now that we're talking about an algorithm, how do I go find negative cost cycles? I mean, I was talking about how they exist and how we can stare at the graph and see them, but do we have an algorithm that can find a negative cost cycle in a graph? And the answer, as it turns out, is pretty clearly yes. So we've seen before that there are ways to detect negative cost cycles. So for example, we could use the Bellman-Ford algorithm. At the end of our coverage of the Bellman-Ford algorithm, so ballparking it, that would have been something like lecture 34, near the end of that, we observed, after we had proved the correctness of the algorithm, that there is a pretty natural way of testing for negative cost cycles. Basically what we do is we run the algorithm for one extra iteration. And if anything changes, the only way something could have changed is if a negative cost cycle exists. Which means if I want to test whether a graph contains a negative cost cycle, I could just run the Bellman-Ford algorithm for one extra iteration. And so the total running time is V times E. And if it reaches this error state where it detects the cycle, then I know a cycle exists. Now, I don't actually care about any of the other things the Bellman-Ford algorithm produces here. I don't care about the cost of paths or the parent array, or at least I don't care about the minimum cost path tree. I'm using the algorithm as a utility to tell me whether a graph has a negative cost cycle or not. That doesn't give us everything we want, though. So we already know from lecture 34 that we can detect negative cost cycles, but how do I find the cycle itself? I don't just want to know whether a cycle exists. I want to know what the vertices in the cycle actually are so that I can perform an augmentation around that cycle. So here is a small variation on the Bellman-Ford algorithm, and I won't give too detailed an explanation of this. There's a lot of ways of getting the same effect. But basically what we're doing here is, because we don't actually care about the costs themselves, we just care about whether the negative cost cycle exists, and then later, how do we get the negative cost cycle? What we'll do is, we'll begin with a cost array initialized to all zeros. Now, if we compare that to the usual Bellman-Ford algorithm, the cost array is initialized to all infinities, because the idea is at the beginning, we don't know that anything is reachable from vstart at all. But in this case, we don't care about vstart. Like we don't care about some minimum cost path tree. We care about, in a sense, hijacking the logic of the Bellman-Ford algorithm to find negative cost paths. And the thing that we have to be careful about here is, we know that the Bellman-Ford algorithm, let's suppose that we chose this vertex as vstart. We know that the Bellman-Ford algorithm relaxes all edges at each step, even edges that aren't reachable from our starting vertex at all. So suppose this is our starting vertex, and over here, elsewhere in the graph, so separated completely from the rest of the graph, there are these vertices. These vertices are completely unreachable from V. But if this is where the negative cost cycle is, I still want to be able to find it. And the Bellman-Ford algorithm does relax all of these edges at each step. It's just that the normal algorithm, the relaxation the normal algorithm performs has no effect, because the costs associated with these vertices are always going to be infinity until they've been reached from G, or from V. However, if I set the cost to be 0 at the beginning of the algorithm, then these edge relaxations can be meaningful. The costs themselves, the actual numerical value of the cost doesn't mean very much. However, if we start by saying, look, the current cost of getting from anywhere to V start is 0, and if that cost ever goes negative, it means there must be some way of wandering around from V start back to itself with negative total cost. In other words, a negative cost cycle. Now, what I've just given isn't a formal justification of that. We don't really need to go. You could, I think maybe you understand enough about it now that if you wanted to prove it, you could see your way towards a proof. This isn't the most orthodox way of finding negative cost cycles if we care about minimum cost paths, but we don't care about minimum cost paths. We're only using the Bellman-Ford algorithm for its one extra feature of being able to find negative cost cycles. And so in this case, if we start with a cost array initialized to 0, if we reach this line here where the negative cost cycle has been detected, we can actually be assured that we've found any negative cost cycle in the graph, even one that was formally inaccessible from our starting point. Additionally, if we get to the point where a negative cost cycle is detected and I want to know the vertices in the cycle, I can actually get those vertices by walking upwards from the vertex where I detected a negative cost cycle. So this detection mechanism occurs if any edge relaxation at the last iteration of the loop modifies the cost of a vertex. And again, go back to lecture 34 to know why that's the reason a negative cost cycle has to exist. So suppose at this step, I discover a vertex V whose cost changes at that iteration. That means there's a negative cost cycle in the graph. It doesn't necessarily mean that V is part of that cycle. I mean, maybe it is, maybe it isn't. But if I want to know what's in the cycle, what I could do is walk upwards from V in the parent array. And here is another fact that I'm not going to directly prove, but you can think about it. It turns out that it's true. If I keep walking upwards at this state, I'm eventually going to reach a place where the parent of a vertex is a vertex I've already seen during my walk. And that means these vertices are the vertices in the cycle. And as I said, I won't give a formal proof of this, but I will explain. We've actually seen this happen at least once before. So consider back in lecture 34 when we first encountered unboundedness, the case where there's a negative cost cycle, and that means the minimum cost path problem doesn't really have a solution, at least as far as we have defined it. In lecture 34, if we look at this slide here, for example, we had tried to create a minimum cost path tree rooted at A. And so that means the parent array is supposed to be a tree rooted at A. But we observed that after we reached this unbounded state, once the negative cost cycle had been exposed, the parent array no longer contained a tree at all. Not only it has a cycle built into the tree, but also the root vertex of the tree is disconnected from everything else. So this is one reason why writing a formal proof of the thing I'm discussing is sort of weird, because what I have to do is begin by proving that this parent array, which no longer refers to a tree, refers to something meaningful. So there are resources out there with proofs of this and so forth. The idea basically is that if the Bellman-Ford algorithm discovers a negative cost cycle, by the end of the algorithm, by the time it reaches this line here, that negative cost cycle will have been embedded in the so-called, we shouldn't even call it a tree at this point, the so-called parent array of the so-called tree. And so if I walk upwards from some vertex, for example, if I walk upwards from D in the tree, I go up to Q, and then up to P, and then up to R, and then back up to Q, and you can see there's the cycle. So I can actually recover the contents of the negative cost cycle from the parent array if the Bellman-Ford algorithm detects the cycle. And so this is all I need to implement my algorithm to find a minimum cost flow. So what I do is I just, at each iteration of the loop, I use the Bellman-Ford algorithm in this amount of time to check whether a negative cost cycle exists. And if it does exist, to find the vertices in the cycle. If the cycle does exist, I then perform an augmentation around the cycle. We already know that because of the way the residual graph is defined, the residual capacity of that augmenting cycle has to be at least, has to be greater than 0. It has to be, and we'll see in a minute that if our flows are integer valued, that means it has to be at least equal to 1. And that's one way that we can show that over time, we are going to eventually reach the minimum cost flow. Because of course, if we're performing a meaningful augmentation at each step, that means the cost has to be going down a little bit at each step. And therefore that we are going to be moving slowly towards the optimal solution and eventually get there. So I again will not go into much theoretical detail here, although this is basically a mirror image of some of the proofs from the last lecture about the integrality theorem. But basically, if all edge costs are integers, then we know that the residual capacity is at least 1, because if the edge capacities are always integers, we know already that every augmenting path has to have capacity at least 1. That means that if all edge costs are integers, that we can guarantee that the total cost of the flow drops by at least 1 at each iteration of the loop. And in a case where there is a minimum cost flow in general, then we can expect we will arrive there in a finite number of iterations. And so the number of iterations is going to be dictated by the cost of the flow that we started with. So suppose that the cost of f is equal to Q. So f is some arbitrary maximum flow. It may have a really, really high cost. It's just some maximum flow. Suppose the cost of a minimum cost flow is, I don't know, we'll call it Q star or something like that. So basically what's happening is we can guarantee, and we can actually maybe even prove tighter bounds than this, but it's relatively easy to guarantee that each iteration of this loop lowers the cost of the flow I'm working with by at least 1. And so what that means is the total number of iterations before I get to my minimum cost is just going to be Q minus Q star. Okay, so that's the total number of iterations of the loop. Now the problem is, I guess we could see our way towards a situation where Q star could be equal to like 0 or something, and Q could be equal to some extremely large number. So because there could be an incredibly large difference between the cost of my initial flow and the cost of my maximum or my minimum cost flow, the loop could have a very large number of iterations, but it's still a finite number that can be parameterized by the cost of that maximum flow that we started with. So I guess that means the total running time of the algorithm is therefore, well, there's the running time of finding the maximum flow that we start with, and then the running time of my loop, okay, well, the augmentation requires this amount of time. We already know that. And finding the negative cost cycle requires this amount of time, the amount of time for the Bellman-Ford algorithm. And the number of iterations of the loop is Q, where Q is the total cost of the maximum flow that I start with. So I end up with this rather unusual looking running time. I'm going to call this algorithm the cycle canceling algorithm. We start from a maximum flow, and we repeatedly, in a sense, cancel negative cost cycles until we're at a minimum cost flow. Okay, so let's try out this cycle canceling algorithm on the network we were working with a minute ago. So a minute ago, when we were doing those examples, we were working with a specific flow of value 5. We never actually found a maximum flow of this network. So let's try out finding a maximum flow of the network and then canceling cycles to make a minimum cost flow. Okay, phase 1. Let's use the Edmonds-Karp algorithm to find a maximum flow. Okay, so I augment here, I augment here, I augment here, I augment here, and then I'm done. Okay, so with that series of augmentations that you're welcome to use for future study, we end up with a flow of value 14, which we know to be a maximum flow because if you take a look at this cut, it has capacity 14, and the total cost of my maximum flow at the moment is $241. Okay, so that brings us to phase 2. Phase 2 is go looking for negative cost cycles in the residual network and then cancel those cycles, perform augmentations along those cycles until there are no negative cost cycles left. Okay, so while GF contains a minimum cost, negative cost cycle P, perform an augmentation that reduces the total cost of the flow. Okay, so as I said earlier, this is the kind of thing that's pretty difficult to do, like the full algorithm on paper, because even finding one negative cost cycle can take a little bit of time in a network that's this complicated. In any event, there is a negative cost cycle T, V5, V3, V4 back to T, and the unit cost of that cycle is negative $21. So I perform an augmentation around that cycle, and I'm able to lower the total cost of my flow to $220. Okay, I go looking for negative cost cycles in the residual network after the augmentation. I find one. Here is a negative cost cycle that has nothing to do with S or T. Its unit cost is $6 or negative $6. It looks like the capacity of that cycle is going to be 2. So that's the maximum number of units I can push through the cycle. Okay, so I perform an augmentation of 2 units around that cycle. That brings me down to $208 in total, so a reduction of $12. All right, and then there's still a negative cost cycle. It's this big cycle here. It has unit cost negative $8. I perform an augmentation, which brings me down to a total of $192. I still have a flow value of 14. And it turns out at this point that no negative cost augmenting cycles exist. And as I said a minute ago, finding negative cost cycles is not very easy, especially, I mean, look at this network. But determining that no negative cost cycles exist is a real pain. So it's nice that we have the Bellman-Ford algorithm to do that for us. So because there are no negative cost augmenting cycles, the flow I'm working with here is a minimum cost maximum flow. So if I want to push 14 units of flow from S to T, the minimum price I have to pay is $192, and I could realize that by using the flow assignment shown here. Okay, so there's some more evidence that the cycle canceling algorithm works, the fact that we were just able to use it to produce our minimum cost maximum flow. But you know, this running time sort of bothers me. So, okay, sure, v times e squared, that's all right, finding the maximum flow. You know, even if this were a big number, like v to the fourth or v to the fifth, that wouldn't be the worst. It does feel like we're solving a pretty difficult problem. The problem that I have with this running time is this number q. So Q is the cost of an arbitrary maximum flow. It's the cost of whatever maximum flow the Edmonds-Karp algorithm finds for me. As I said a minute ago, the cost of the maximum flow that we start with and the cost of the minimum cost maximum flow could be very different. And we know already that what we have here is a running time that's sort of parameterized by something that we don't know in advance. Like, we don't know the minimum cost of a maximum flow. We don't generally know anything about a maximum flow before the algorithm starts, so we don't know the value of Q. I would argue that this is actually even worse than our last example of an output-sensitive algorithm. So in a previous lecture, so 2 lectures ago or 3 lectures ago or something, we saw that the generic Ford-Fulkerson algorithm has this running time. So number of edges multiplied by the value of a maximum flow. And I said at the time that that's sort of dangerous because we don't know the value of a maximum flow in advance. We have an output-sensitive algorithm parameterized by one of the output parameters. I would argue that this situation is actually even worse because this value Q isn't the cost of a minimum cost flow. It's not the value of a maximum flow. This is just the cost of some arbitrary maximum flow. So it's not even really output sensitive. It's sensitive to some sort of arbitrary parameter that's vaguely related to our output. And so I think that's actually even worse than the output sensitivity of the Ford-Fulkerson algorithm. So there's one reason that we should have some motivation to try and find a different algorithm. But in any event, we have now found an algorithm to compute minimum cost maximum flows. So I guess the question before we go further, because the next thing we have to do once we have minimum cost maximum flows is to see if we can find a way of now solving things like the transshipment problem. And it turns out that we can. But before we do that, the question is, can we do better on the algorithm front? Can I come up with an algorithm that, even if it's output sensitive in its running time, it's not sensitive to a parameter like Q here, because I'm sort of uneasy about this dependency on Q. Okay, so I mentioned earlier that there was a sort of fork in the road about how do we find a minimum cost maximum flow. The first idea we started with, the idea that led us to the cycle canceling algorithm, was to start from any maximum flow and then go through a sequence of different maximum flows, each with a lower cost than the previous one. We keep canceling out cycles to bring the cost down, but we keep the value the same. We still have a maximum flow, but the cost gets lower and lower until we reach the minimum cost maximum flow. But another idea might be start from any minimum cost flow and then work your way up through larger and larger values until you reach a maximum flow. So I guess the idea then is, instead of refining a maximum flow f to incrementally decrease the cost, start from a known minimum cost flow, which may not be a maximum flow, and then increase the value of the flow until the flow is maximum. That's the other way of approaching this. Okay, so I have got this flow from earlier. Recall earlier that we came up with a flow of value 5 with total cost 30. And we found that this particular flow of value 5 was a minimum cost flow. So that's why I'm using the flow that we found earlier. We already know that this flow is minimum cost. We also know that this is not a maximum flow, because on the same graph just a minute ago, we found a flow of value 14. So here we have a non-maximum flow that is minimum cost. Now consider this path here. And I mean, where did I get this path from? I will tell you, take my word for it, I guess, but you can check this if you want. It turns out that of the various paths in my residual network, the path that I've chosen is a minimum cost ST path. It's rather circuitous, but this happens to be a minimum cost path from S to T in the residual network. Recall that every path from S to T in the residual network is an augmenting path in the original network. And a minimum cost path from S to T in the residual network is the kind of thing I could compute with a minimum cost path algorithm, like Bellman-Ford or the Floyd-Warshall-Roy algorithm. We'll see in a minute that Dijkstra's algorithm isn't going to work in general in this case because there could be negative cost edges. Actually, well, here's a negative cost edge here. I'll just make that point now. Because our residual network could contain edges corresponding to pushing flow backwards, which therefore have negative costs, I don't want to use Dijkstra's algorithm to go find minimum cost paths. So what I found on the right is a minimum cost path from S to T in my residual network. So suppose I use that as my augmenting path. I perform an augmentation along that augmenting path. I end up with a flow of value 7 and total cost 46. An observation I can make, or even better yet, I could have an algorithm make for me, is that in the residual network that results, there are no negative cost cycles. In other words, after performing an augmentation along a minimum cost augmenting path from a known minimum cost flow, the flow that I end up with is also a minimum cost flow. So it turns out that if you take a minimum cost flow that you already know is minimum cost and you augment it along a minimum cost augmenting path, the resulting flow also has minimum cost. And that's a theorem that we can sort of prove. I'm going to give a proof of it that I think that I'm not the most confident in. I think it has a couple of little gaps that need to be filled in. But I think it does give us, this is a theorem we can at least explore via some kind of proof. Okay, so Theorem B says, suppose you have a flow network with associated edge costs, and suppose you know that flow F is a minimum cost flow of some value. If I then go and find a minimum cost augmenting path, that is to say, any minimum cost ST path in the residual network, the flow that I get from performing that augmentation is a minimum cost flow. So there are lots of theorems, there are lots of proofs of this theorem out there, and most sources that prove this theorem use linear programming theory. They use like duality of linear programming, which is lots of fun, but it's not really any of our business in this course. There is this pleasant graph theoretic proof that I'm going to present here, which isn't my own work. It is adapted from this book, which is the primary source for most of the progression of this lecture. And the proof in this book is, to be honest, a little bit sloppy. So earlier I cast some shade on another proof, on a proof of Theorem A, and it was actually also the proof from this book. So this book has a proof of Theorem A that I consider to be rather sloppy as well. I want to walk through the proof. I've tried to fix a couple of holes in it, but there's still some ambiguity. In any event, there are plenty of proofs of this theorem using higher level linear programming theory that we don't understand ourselves, but that I think do prove the theorem a lot more soundly. Okay, in any event, let's take a look at this proof. So consider, suppose we have the conditions of the theorem met. So I've got a minimum cost flow F, and now let's consider some minimum cost ST path in my residual network. So a minimum cost augmenting path. Suppose I perform an augmentation along that path, and the flow that I end up with isn't a minimum cost flow. So I'm going to go for contradiction here. Now, by Theorem A, obviously, if the flow I end up with is not a minimum cost flow, there must be some negative cost cycle somewhere in the graph. Okay, so the first argument I want to make is that if there's a negative cost cycle in F prime, that negative cost cycle has to be tangled up in my augmenting path. So I have my augmenting path, and I'm going to argue that it is not possible for the negative cost cycle that I end up with to be somewhere completely different in the graph. So the claim is, for at least one edge along my augmenting path, the reverse edge needs to be part of my negative cost cycle. So the cycle and the path have to touch. And in particular, they have to touch in such a way that the cycle edge is the reverse-oriented version of the edge in the path. And the reason is basically that if the two things were disjoint, so in other words, if the negative cost cycle were somewhere off in the distance, that means that the negative cost cycle had to have been there before. Because obviously, if the path itself doesn't touch the cycle, then the negative cost cycle wouldn't have changed at all as a result of the augmentation. But that's impossible because we defined the flow that we started with to be a minimum cost flow, which means that F does not contain any negative cost cycles. The only way a negative cost cycle could have been created by an augmentation through P has to be if that cycle involves one of the edges that was created in the residual network as a result of the augmentation along P. And actually also, furthermore, so I push some flow along the edge pi plus 1. In the residual network, that will open up the possibility of using this edge. So that's why I'm arguing that the edge has to be an edge with reverse orientation. Okay, so basically what I've now shown is that the cycle and the path overlap in some sense. That is, there's an edge of the cycle that goes backwards where the path goes forwards. They overlap at these two vertices. Without loss of generality, just to make the numbering easier, so I gave the cycle an arbitrary numbering. Let's just assume that I chose a numbering such that the vertex pi was the first vertex in my cycle, and the vertex pi plus 1 was the last vertex in my cycle. So the cycle goes pi, then c2, and then around to cl minus 1 over to pi plus 1. All right. So now let's consider what would happen if I start at S and I walk all the way to pi, and then I walk all the way around to pi plus 1, and then over to t. And I'm doing this in the graph before the augmentation. So I haven't done the augmentation yet. I'm following all of the edges of the cycle, excluding that edge that I argue was maybe created during the augmentation. Let's just consider the cost of this walk. So this is not necessarily a path. I have no guarantee that somewhere there isn't some other overlap between the cycle and the augmenting path elsewhere. So all I can say is this is a way of walking through my graph. So what I do is I walk from S to pi, around the cycle to pi plus 1, and then over to t. What is the cost of that walk? Okay, well, what I've really done is I've taken all of the edges along P, except for this one, and I've taken all of the edges along the cycle, except for this one. So I can say that the cost of the walk is the cost of the path P minus the cost of the edge from pi to pi plus 1, and then I add the cost of the cycle minus the cost of the edge from pi plus 1 to pi. Okay, so I'll rearrange terms a bit. I have cost of P plus cost of C minus this. But remember that the cost of pi to pi plus 1 and the cost of the reverse edge are just the negatives of each other. They just cancel each other out, which means the cost of my walk is the cost of P plus the cost of C. And the issue is, we already said that C was a negative cost cycle. That means that the cost of P prime is actually going to be less than the cost of P. So what I've shown is, before augmentation, there is a way of getting from S to T that costs less than my minimum cost augmenting path P. Now, the proof in the book that I cited stops here and says that's a contradiction. And I'm not quite convinced about that. The issue is that we could have been writing a proof about augmenting walks or something, but we're writing a proof about augmenting paths. And all I've shown is that I have a walk of lower cost than my path. This doesn't necessarily by itself guarantee that there is a lower cost augmenting path. And to get a contradiction, I have to show that there is a path with lower cost than P. Okay, so that's annoying. So that's sort of a loose end I have to tie up. So basically, I didn't rule out the case where the cycle and the path overlapped in a bunch of other places, which means I can't conclude that the thing I just came up with, this complicated thing P prime, that this is actually a path. So I don't think I yet have a contradiction. However, as it turns out, we've already proven a theorem elsewhere that allows us to take that last step. So what I've shown is that there exists some walk in my graph, in my residual network, that has lower cost than my minimum cost augmenting path. What I can show via a theorem from lecture 34 is that as long as I have a walk of a particular cost in a network with no negative cost cycles, and we know that the network has no negative cost cycles before the augmentation because it's a minimum cost flow, if I have a walk with a particular cost and there are no negative cost cycles, there must be a path with that cost as well. So in lecture 34, there was this theorem, Theorem A, that was used as part of the proof of correctness of the Bellman-Ford algorithm. Now, if you're just coming from the video version of lecture 34, you might stare at this and say, wait a minute, that's not what Theorem A looked like in lecture 34. That's right, I revised it. And so the version that was done in class, in the meantime, we refined it a little bit to change the bounds because the statement of Theorem A in the video version of lecture 34 was rather sloppy because it was talking about things like minimum cost walk walks in a graph that might not have a minimum cost walk because the minimum cost could have been negative infinity. In any event, this is a revised version of the theorem that proves the same thing. What the theorem ultimately tells us, so we use this property for a different reason in the context of the Bellman-Ford algorithm, but it is relevant here. What the theorem tells us is that if you have a minimum cost walk with the fewest possible edges, and that isn't a path, then the graph must contain a negative cost cycle. And in our case, because we're talking about the residual network of a flow corresponding to a flow that doesn't have any negative cost cycles because it's a minimum cost flow, we can actually use the theorem because the theorem then implies that if the graph doesn't have negative cost cycles, the minimum cost of a particular path has to be less than or equal to the cost of any walk from between those two vertices. Because basically, if the minimum cost walk between two vertices wasn't a path, that means it must repeat vertices, and if it repeats vertices, the theorem tells us there's a negative cost cycle. Okay, so that's actually sufficient to say I've found this walk that has total cost less than my minimum cost path. Okay, and the theorem tells us that because the graph contains no negative cost cycles, there must exist a path with cost less than my minimum cost path, and that's the contradiction that we're looking for. And that's enough to prove Theorem A. So therefore, if I have a minimum cost flow f, and I augment that flow along a minimum cost augmenting path, the flow I end up with is a minimum cost flow. And that's sufficient to bring us to another algorithm to find minimum cost maximum flows. Instead of starting from a maximum flow and canceling cycles, I start from any minimum cost flow and I keep augmenting it along minimum cost augmenting paths. And what's nice about this algorithm is almost the same as the Ford-Fulkerson algorithm. It is almost a regular variant of the Ford-Fulkerson algorithm where I'm just choosing my augmenting path carefully. So the algorithm starts from any minimum cost flow. Now, in the case where the original network has no negative cost cycles, so we know by now that negative cost cycles in a flow network aren't necessarily the end of the world. We can resolve them, as we saw with the cycle canceling algorithm. In the case where the original network doesn't have any negative cost cycles, the all-zero flow is a minimum cost flow, which means what we could do is just start off from a flow assignment of all zeros and do a bunch of augmentations. That's exactly what the Ford-Fulkerson algorithm does. The only real difference is I have refined the logic that selects augmenting paths. Now, one thing also to consider is it is valid. There are ways for a flow network that has negative cost cycles to have a minimum cost maximum flow. But the key thing is if the graph has negative cost cycles, the all-zero flow may not be a minimum cost flow. So just as an exercise, try that out. Show off that that is the case. So suppose now that we focus for the rest of this lecture on the case where the network that we start with does not have negative cost cycles. If that's the case, then we can start with this algorithm from an empty flow, that is with all edges assigned a flow of 0, and then perform a sequence of ordinary augmentations where the augmenting path that we choose is a minimum cost path, in the residual network GF. And what you'll observe is this is, and I know this because I literally copied and pasted it, this is the Ford-Fulkerson algorithm, but with one refinement, which is where I choose my augmenting path by certain logic. So I might use the Bellman-Ford algorithm to find the augmenting path. And as I mentioned earlier, if the graph contains bidirectional edge pairs with different costs, so if I have a situation like this, so I've got a cost of $5 in this direction and $10 in this direction, the problem is still solvable. You can still develop an algorithm to solve the problem. However, this augmentation logic won't work. You do need to specialize the augmentation logic a little bit. Basically, what you have to do is to perform two separate augmentations. If you find yourself in a position where you're pushing some flow backwards along an edge and also pushing flow forwards along an edge in the forwards direction at the same time. That's all. So this pseudocode is oversimplified for that case. So we're going to continue for the rest of this lecture assuming that there are no bidirectional edge pairs with distinct costs. So the algorithm that I just outlined, which as I've mentioned is effectively a straightforward variant of the Ford-Fulkerson algorithm, I actually didn't know about this way of doing things until I began preparing these lectures. That is, most of my experience with minimum cost minimum cost flows has been in the context of linear programming, and so I mentioned earlier I might use the network simplex algorithm for that. So I went to look up exactly where did this approach come from? Like, who invented the idea of augmenting along minimum cost paths and first proved that it worked. And that led me down this bizarre sort of garden path. So I was eventually able to find some sources that cited other sources as the inventor of this technique. And in general, it appears as if this approach is cited as originating with this paper by our old friends Edmonds and Karp. So that's sort of neat. What's even more interesting about this is the same paper where they proposed the Edmonds-Karp algorithm. And actually, that's going to prove to be a little bit of a difficulty for us. Like, what are we going to call this algorithm? So back 2 lectures ago, in lecture 38, we proved that a particular maximum flow algorithm was polynomial time. And we've been calling it the Edmonds-Karp algorithm. And that is the right name. I mean, that is the name everybody calls that algorithm. The Edmonds-Karp algorithm is an algorithm to find a maximum flow in polynomial time. But in the same article as where they proposed that algorithm, they also proposed the idea of augmenting along a sequence of minimum cost paths. So we can't call the algorithm that we just came up with the Edmonds-Karp algorithm because, that's a name that we're already using for something else, something very closely related. Okay, so what do we do? Well, actually, if you look at Edmonds and Karp's paper, so here is their equivalent of our Theorem B, the theorem that we proved a minute ago, which was if you have a minimum cost flow, which they call an extreme flow, which sounds pretty cool. If you have a minimum cost flow and you augment along a path of minimum cost, they've said minimum weight, fair enough, then the flow you end up with is also a minimum cost flow. So they have a theorem that is equivalent to our Theorem B. And you could argue that this theorem really is the core reason why the algorithm works. This theorem is responsible for the algorithm. So we can't call the algorithm we just came up with the Edmonds-Karp algorithm because, the name is taken. How about this? Let's figure out where they took this theorem from and then name the algorithm after those people. Okay, but it turns out that they cite the theorem to Ford and Fulkerson. It turns out that this theorem was actually proven via certain logic in the book Flows in Networks by Ford and Fulkerson. By my recollection, the proof in that book is very linear programming-ish. So it doesn't use a graph theoretic interpretation. It's a very linear programming-based proof. Okay, so I obviously can't call the new algorithm the Ford-Fulkerson algorithm because that name is taken as well. Okay, so what do I do? Well, there are a lot of sources that observe that what you're doing here when you're augmenting along these minimum cost paths, you'll recall that this term minimum cost path is a sort of thing that I do but isn't that common in other sources. Many sources call the minimum cost path problem the shortest path problem. So a lot of sources call this algorithm the successive shortest path algorithm because it repeatedly augments the flow along shortest paths with minimum cost. But you see, I have a problem with that because, wait a minute, the Edmonds-Karp algorithm, that polynomial time algorithm to find maximum flows, is also a successive shortest path algorithm because it uses augmenting paths found by BFS. And we all know that the paths you find with BFS, the paths from the root of a BFS tree to other nodes, are shortest paths in a graph theoretic sense. And I'm going to argue that this is the vindication that I've been waiting for. This is why calling it the shortest path problem gets confusing because shortest path can mean a lot of different things. And in particular, we already know that a short path in a graph is often just short in terms of the number of edges. And so what we have discovered is that Edmonds and Karp in 1972 published this one paper where they proposed 2 different flow algorithms that were both based on different interpretations of shortest paths. And they were able to solve different problems, although it turns out that the running times of the 2 algorithms were also different. So good for them. A lot of authors these days, quite cynically, if they have 2 different algorithms to propose, would publish 2 different papers, or even worse, break it up into like 5 different papers. So good for Edmonds and Karp for publishing such a valuable paper. In any event, we're going to call this thing the successive minimum cost path algorithm. Okay, so since when I go looking for my augmenting path, I'm looking for a minimum cost ST path in the residual network, well, we know that there are edges in the residual network that could have negative cost. And that means I can't use Dijkstra's algorithm because it completely rules out the use of Dijkstra's algorithm because Dijkstra's algorithm doesn't work with negative cost edges. And so I could use the Bellman-Ford algorithm. Great. So I use the Bellman-Ford algorithm to find a minimum cost augmenting path in this amount of time, V times E. Now I should add, we're not going to cover them today, but there actually are ways to adapt this approach by fiddling around with the values of costs, basically, such that you can use Dijkstra's algorithm. So there's some pre-processing steps you can do such that there aren't any negative cost edges after all, and therefore you can use Dijkstra's algorithm. And that's a good idea. It does bring down the running time. We're not going to talk about it in detail, though. Okay, so because the successive minimum cost path algorithm is a special case of the Ford-Fulkerson algorithm, we get to recycle all of the results on running time and correctness of the Ford-Fulkerson algorithm, because the Ford-Fulkerson algorithm just says find any augmenting path, and all we're doing is saying find a specific augmenting path, which means we know this algorithm will get us to a maximum flow. We also know quite a few things about its running time. We know that the running time of the generic Ford-Fulkerson algorithm is this, and therefore that the running time of our algorithm is going to be related to this, although I do have to fold in an extra term to account for the running time of the Bellman-Ford algorithm. And so the total running time of the successive minimum cost path algorithm is therefore this number, V times E times the value of a maximum flow. Now, although this is obviously still an output-sensitive algorithm, I would argue that this is way less of a hazard than the earlier cycle-canceling algorithm, because at least this one depends directly on the value of the maximum flow, so some directly observable property of the output, not some parameter of some intermediate value in the middle of the algorithm as we had with the cycle-canceling approach. All right. We already found a minimum cost maximum flow of this network, but let's do it again using the successive minimum cost path algorithm. Now, the network that we're starting with, notice that this network has no negative cost edges in it to begin with, which means we can use the basic algorithm that starts from the all zero flow right off the bat. If the graph contained any negative cost edges, we would first have to do something to get us to any minimum cost flow. We could, for example, do cycle canceling on the zero flow or something. We have to get to a minimum cost flow of some kind before we can employ our successive minimum cost path algorithm. But because this graph has only a non-negative costs, we can start directly from the zero flow. Okay, so the first minimum cost augmenting path is the path P, V1, V3, V4T, which brings us to a cost of $30 and a value of 5. The next augmentation brings us to a cost of $46 and a value of 7. Then we're up to a value of 10 and $73. We do this augmentation, get us to a value of 11. We do another one to get us to a value of 12. We get to 13, and then we get to 14 via this augmentation here. And we know from earlier that actually the value of the maximum flow in this graph is 14. We also know from our earlier example that the minimum cost maximum flow has cost 192. And if we observe that there are no augmenting paths available, we know that we have a maximum flow. We know from Theorem B that the flow is minimum cost. So we've now found a minimum cost maximum flow of this graph by two different methods, by the cycle canceling algorithm and by the successive minimum cost path algorithm. All right, so I guess for completeness, we were talking last time about fire prevention and observing that this vertex T has this nasty tendency to catch fire. And to avoid that ever happening again, what we ought to do is to route as much water from vertex S to vertex T as possible. Let's make sure T is always soaking wet. And I observed at the end of the last lecture that unlike when we were putting out a fire, we do actually have to consider the cost of that routing. So what I want to do is find a minimum cost maximum flow for this flow network, the one that we started with where that vertex used to be on fire. Now notice that the network does not contain any negative cost edges, and therefore there's no way that we're going to have to worry about negative cost cycles showing up, and so the all zero flow will be a minimum cost flow. Okay, so I choose a sequence of minimum cost augmenting paths, and it's harder to see these without the residual network, so I'll just run through them. You may have to, if you want to practice with this example, it might be a bit harder than the previous example where you could see the residual network. We start with this augmentation for a value of 5 and a cost of 40. We get to a cost of 70 and a total value of 7. There's a value of 10, cost 121. Value 15 costs 281. And then finally a value 16 at a cost of $314. And we know at this point that no further augmenting paths are available. We can see, if we look at the capacity of this cut, that the cut has capacity 16, and therefore we know that our flow is maximum. And we also know, because of the augmentation strategy that we used, that we have a minimum cost maximum flow. Now, so we've finally tied up that loose end. We've been able to both put out the fire and ensure that the fire doesn't start again, we only have one remaining loose end to tie up with our study of flow networks, which is, back at the beginning of this lecture, I was talking about the transshipment problem, a problem that quite visibly is rather different than the maximum flow problems that we're used to. In the meantime, we have figured out that cost-related flow problems, cost minimization, actually can be done in the framework of the maximum flow style flow networks. However, it is still sort of weird to think that the transshipment problem, which is a different kind of minimum cost flow problem, can actually be framed with the traditional flow networks that we've been working with that are geared towards maximum flows. But it turns out that it can. And doing so, turning the transshipment problem into a maximum flow problem, has a lot in common with some of the things we did in the previous lecture regarding our graph of different types of refreshments. We're taking a graph and then adding source and sink vertices and synthetic edge capacities to realize a particular effect. So what I do is I take a transshipment instance, so here is a transshipment instance where every edge has a cost but no inherent capacity, and every edge has a supply value, which could be positive or negative. And I know in advance, because the instance is not considered valid otherwise, that the total surplus of the graph is equal to the total shortage. Now, for the sake of the diagram looking nice, I've decided to put all the surplus vertices on the left and all the shortage vertices on the right. But of course, in general, they can be anywhere in the graph. So what I do is I add an all-purpose source vertex over on the left. I add an all-purpose sink vertex on the right. I connect the source vertex to every vertex that has a surplus. I connect all of the shortage vertices to the sink vertex. And it has to be done this way. I don't connect the source vertex to the shortage vertices, and I don't connect the surplus vertices to the sink vertex. And then, of course, I need edge capacities before I have a maximum flow instance. So what I do is I add an edge capacity of infinity to all of the edges in the original transshipment instance, because we know in the transshipment problem, there are no inherent edge capacities. Now, edge capacities of infinity are fine, although I do have to be a little bit careful, because if ever I end up in a situation where there's a path from S to T, where all of the edges have infinite capacity, then the problem has no solution. But in this case, I don't have to worry about that because I do add finite capacities on every edge leaving S and every edge entering T. And it's using these capacities that I'm able to encode the supply values into my maximum flow problem. Because the maximum flow problem with edge costs only cares about things like the flow value, the capacity, and the costs along edges. Things like the supply value need to be factored in manually. I have to find some way of adapting them into the problem. And so what I do is this. I take a look at V1. V1 apparently has a surplus of 10 units. Now that's in the transshipment instance. In the maximum flow problem, the source vertex S is the only place where flow can originate, and the source vertex has an infinite amount of flow. So what I'll do to model V1 having a surplus of 10 is I'll add an edge from S to V1 with cost 0 and capacity 10. If there's any way of moving 10 units out of V1, then I'll be able to take all 10 of those units from S for free as needed. Now similarly, vertex V9 has a shortage of 15. Well, of course, in a maximum flow problem, the sink vertex T is the only place that flow is allowed to end up. So what I'll do is add an edge with capacity 15 from V9 down to T with cost 0. So if there's a way of getting 15 units to V9, they'll all just be sent down the drain at vertex T. So that therefore I achieve the balance I need for my maximum flow problem. So I guess what I'm saying is if there's a way of resolving all of these surpluses to bring all the associated flow to the associated shortage vertices, then I can get the flow I need from S, bring it to the surplus vertices. I can send it through the network by whatever means I want to get it to the shortage vertices. And if I notice when I'm done that all of these edges are saturated, well, that means that all of the units of surplus at these vertices are being used. And if I notice that all of these edges are saturated, that means that all of the shortages at these vertices are being resolved. Because if this edge is saturated, it means 15 units of flow must be reaching vertex V9. And also, because of the conservation constraints that are inherent to maximum flow problems, I know that all of the units of flow leaving vertex S have to reach vertex T. And so if 10 units of flow leave vertex S and get to V1, and 15 units of flow leave vertex V9 and get to T, that means that V1's surplus is being realized, all 10 of those units are going to good use, and vertex V9's shortage is being satisfied. All 15 units that V9 needs are somehow entering vertex V9. So basically the framing amounts to, if once I've done this construction, a maximum flow saturates every edge leaving S and every edge entering T, then there exists a feasible solution to the transshipment instance. That is, there is a way of balancing flow to balance out supply and demand across the graph. And that means that if I then find a maximum flow with minimum total cost, then I have found the optimal solution for my transshipment instance, the solution that minimizes the total cost of balancing supply and demand. So we now have an algorithm to find minimum cost maximum flows. I've figured out a way of adapting a transshipment instance, a minimum cost flow problem, to be a maximum flow network. So we can now solve the transshipment instance using algorithms that we have. So we'll use the successive minimum cost path algorithm to do this. I don't try to play favorites, but I guess it's pretty clear that this is my preferred, of the two approaches, this is my preferred algorithm. Okay, so here's our first augmenting path. I'll just skip through all of these. You can look at them if you want to practice this later, though. Okay, so we reach a state where we found a flow of value 20, and it is the maximum flow. So we know that the flow produced by the algorithm is a maximum flow. We also know that it is a minimum cost flow, so that we can get 20 units from S to T at a cost of $295. Now the question is, does this mean the transshipment instance is solvable? Well, notice that all of the edges leaving vertex S are saturated. So that is, vertex V1 is getting 10 units of flow, and we know by the conservation constraints that all 10 of those units are getting to vertex T. Additionally, the only way they can get to vertex T is via one of the shortage vertices. And we can then observe, as a mirror image of the source case, that if I look at the edges adjacent to the sink, all of them are saturated. That means that V9 needs 15 units of flow, and it's getting all 15 units. So the surplus at V1 is being realized, the shortage at V9 is being satisfied, and same with the shortage at V10 and the shortage at V11, which means I have found a routing that balances supply and demand, and even better, I have found the minimum cost such routing. Let's try a couple of other instances of the transshipment problem. Okay, so here is another valid instance of the problem. We can verify that the global supply matches the global demand. So I adapt this to become a maximum flow network by adding a source vertex connected to all the surplus vertices and a sink vertex to which I connect all of the shortage vertices. And then I add edge capacities of infinity along all of the internal edges. And then the capacity along the edges leaving S equals the surplus at the destination of the edge. The capacity of the edges entering T equals the shortage at the source of the edge. I perform a bunch of augmentations using my successive minimum cost path algorithm, and I reach this state here. In this state, in my maximum flow, my minimum cost maximum flow, I am paying $38, and I am realizing the surplus at every surplus vertex, and I'm satisfying the shortage at every shortage vertex, and so I know that this does comprise a solution to the underlying transshipment instance. And I guess you could go verify that. I guess I should have said that earlier. You can take a look at the assignments of flows along edges and verify that indeed supply and demand are being balanced. Okay, so we now know this is a solution to my transshipment instance that I was able to solve via a variant of the Ford-Fulkerson algorithm. And then, so if I then strip away, if I get rid of S and T, we can then observe, and I ignore those infinite edge capacities, we can observe that I am able to fully resolve supply and demand in this instance. All right, so a few final cases. I want to talk about cases where the transshipment instance wasn't feasible or wasn't valid. So this is actually an input that earlier we said wouldn't be valid at all. So notice how the global supply is 13, but the global demand is 8. And back at the beginning I said this means we just don't even try solving this. There is no solution. There are extensions of the problem where there's a solution, but this isn't one of them. There is no solution at all. As an experiment though, I want to see what happens if we apply our flow network construction construction to it. So I add my source vertex and sink vertex, I set my edge capacities, I'll perform all the augmentations. I end up with this situation here. So notice that our condition for the transshipment instance to be solvable is that every edge out of S is saturated, every edge into T is saturated. But that condition doesn't hold in this case. There's an edge out of S that's not saturated. So even with the flow network construction, there is evidence that this doesn't comprise a valid solution to the transshipment instance. Now, the reason in this case is because the transshipment instance wasn't valid to begin with. And so we can say, therefore, we do not have a solution. The instance is not solvable. Okay, so this is a valid transshipment instance, but it's infeasible. So the global supply is 8, and the global demand is 8. But observe that I have this vertex V1. We actually saw this graph earlier. I have this vertex V1 where there are no edges leaving V1, even though V1 itself has a surplus, which means I'm going to have a problem because there's no way to resolve that surplus. So I build my flow network construction, I perform some augmentations, and I reach a maximum flow pretty quickly. But in the maximum flow, I observe that there are edges that are leaving S that aren't saturated. And that means that there is no solution to the problem. The maximum flow only translates to a solution to the transshipment instance if every edge out of S and every edge into T is saturated. And in this case, I have an edge out of S and both edges into T that aren't saturated. And what's happening is the 5 units that I want to get rid of from vertex V1 can't be moved, and that means that I can't fully satisfy the shortage at these other vertices that depend on those 5 units. And so we can now say that the underlying transshipment instance is infeasible. It has no solution whatsoever, so it doesn't make any difference to think about the minimum cost of a solution because there's no solution at all. Now, this transshipment instance is feasible. There is a way of balancing supply and demand. We saw this one earlier as well. The problem is there is a negative cost cycle, which means it doesn't make sense to ask about the minimum cost because the minimum cost, in a sense, is negative infinity. And so if I try to compute such a thing, so if we take a look at this, what we can observe is that there is no minimum cost flow. It doesn't make sense for a minimum cost flow to exist. And that means that if I find a maximum flow, it will still correspond to a feasible solution to my transshipment instance, but it doesn't make any sense to talk about a minimum cost maximum flow because I can make the cost as low as I want. Currently the cost is negative 40, but if I wanted to, I could push 1,000 units around the outside of this cycle, and then I end up with an even lower cost flow. And I could just keep doing that. So I can make the cost as low as I want. And that's also a case where the underlying transshipment instance is not balanced. Okay, so that's our coverage of network flows. We are now experts on network flows. And actually, I didn't want to say this at the beginning because it would be too sad. This is the last original algorithm topic that we're covering. The next couple of lectures are basically us flying down the home stretch and talking about what we've learned. So before I talk about that, we now have ways of computing maximum flows. That would be the generic Ford-Fulkerson algorithm, which, I mean, to be honest, if all you want is a maximum flow, the generic algorithm doesn't have much going for it, so I tried to say some positive things. It has this running time that's output sensitive. I suppose in cases where you know that in advance that the value of the maximum flow is very small, maybe the Ford-Fulkerson algorithm could be sort of fast. And also, the Ford-Fulkerson algorithm gives us a lot of flexibility. We've used that to great effect. We've used that to create lots of variants of the algorithm to solve certain other things. For example, this algorithm here that we just saw. So for regular maximum flows, you probably want to use the Edmonds-Karp algorithm, which gets rid of the flexibility because you have to compute augmenting paths by a certain technique. But on the other hand, you are guaranteed polynomial running time, which is pretty good. Should you want a minimum cost maximum flow, and we observed at the end of the lecture that even if you just want a minimum cost flow and you don't care about the maximum part of it because you can always set edge capacities to be infinity, you can use either the cycle canceling algorithm, which does allow for the case where the input graph contains negative cost cycles, but also has this really bizarre running time that's hard to classify that makes me sort of uneasy, or you could use the successive minimum cost path algorithm, where the running time is similar to the original Ford-Fulkerson algorithm, but where you're not allowed to have negative cost cycles in the graph you start with unless you do something beforehand by way of pre-processing to get rid of them. So we're now experts on network flows, and over the past, I guess it's been 40 lectures, we've seen a whole ton of different algorithms. So what have we learned? What do we talk about now? Well, actually, there has been one recurring theme that's come up over and over again, which is that there are some problems that are hard. and there are some problems that aren't. And this has happened repeatedly. Even in the previous lecture when we were talking about a vertex cover, we found that we could find a vertex cover of a bipartite graph rather efficiently. But if we want a vertex cover of a general graph, for some reason that's very difficult. And we've seen other problems over the course of this series of lectures, things like the subset sum problem and the partition problem, that don't inherently look very scary, but for some reason are very difficult. And we now know enough about algorithms, we have a broad enough sampling of algorithms behind us that we can finally address that problem head on. What is a hard problem? And what is an easy problem? And what makes hard problems hard? That's the thing we're going to talk about in the next lecture. And then after that, we have to go even further and say, are there problems that we can't even solve at all?